Ah.
Quente.
Muito abafado.
Seco e abafado.
Muito.
É quente.
Muito abafado. Muito seco, abafado. Good morning.
Good morning.
Nine 41. Yeah. Let's start recording. Interesting. Okay. So we are done with chapter 2. We did freely falling bodies. It's just free fall bodies. Freely falling bodies, nothing but uniformly accelerated motion downwards at 10 meters per second square at the acceleration of gravity. And now we are going to get into scalars and vectors. Okay, here you go. Let me take it out of here. The nature of physics, I would say that the building blocks of physics is part of this chapter here, even though they don't have in there. But that's where I would fit the building blocks of physics. Units like covered. Okay, the role of units problem solving I also covered because it's dimensional analysis, and trigonometry is a prerequisite for the course. Okay, now let's start talking about vectors. At this point, you should already have a qualitative idea of vectors. And what is a vector exactly, right? A vector is like a fancy type of number. It's a different type of number. A number that has something else attached to it. Okay, is a concept in mathematics that's very useful. And whereas numbers have only the concept of intensity of a given value, right? The vector also has information about its intensity, but it has another type of information that is the direction of that idea, of that definition. That's what a vector is all about. And here you go. I have this paragraph here to summarize what I just said, vector is a type of number that has an additional piece of information. Whereas numbers tell you just the magnitude of something, a vector has information on the magnitude and direction of something. Let's emphasize direction here. Okay. So it's a more complicated concept because it carries more than one information. And in physics, we have numerical quantities that we call scalar, as well as vectorial quantities. Not every physical quantity is a vector. Okay, and just go back to the core principles of physics, right? Just to remind you, we have the basic quantities. They are not vectors. They are scalar quantities. When you talk about meter, you do not say what's the direction of the. When you talk about the length, you do not say what's the direction of the length. Okay, it's just the length, just a scalar value attached to it. The same thing happens to time. We do not say what's the direction of time or mass. Okay, but when you talk about position and force, they are vectorial quantities. We come and say, no, a position has a magnitude and a direction attached to it. We usually represent the position vector by the letter R, either with the arrow there at the top or a bold-faced letter R. Okay, I prefer in this most. Let's see, every time that we do some lecture, right? We use this notation here with the arrow at the top. Okay, if you don't have an arrow there at the top, it's not a vector. It's a scalar. And many books adopt this notation for the vector, the bold-faced letter. But again, we are going to be using this notation here for a vector. Here's the position vector, and here's the force vector. This is either a push or a pull. We're going to get into force in more detail later on. And finally, we have the laws of nature, which you didn't cover yet. We're going to see them later when we start talking about force. Okay. And now that we introduced that the idea of vector, let me show you what are going to be the representations and also what are the possible types of vectors, right? Oh, scalars. There you go. Scalars and vectors. Examples of scalars and vectors. Length, time, mass, distance, speed. They are all scalars. And vectors, position vector, the very first one. The force vector, displacement is a vector, velocity is a vector, and acceleration is also a vector. Do you remember that I told you in free fall, during a free fall, the acceleration of gravity, the vector acceleration of gravity is downwards, right? The vector acceleration of gravity is always towards the center of the Earth. Whether we are talking about here the planet Earth or any other planet, it's always towards the center of the planet. When we are talking about a place nearby the planet's surface, that gravitational acceleration vector is going to be in the vertical direction. Okay, velocity. Let me put here gravitational acceleration. And then I will represent by the letter G with an arrow there upstairs. Here you go. Like that. By the same token that we can operate this number and scalars, How do we operate with numbers and scalars? Okay, some we subtract, we multiply, and we divide. We can also operate with vectors. We can also do operation. We can also do operations with vectors. And the operation with vectors is going to be slightly different from the operation that we do with numbers. It's slightly different. No, I would say very different. Okay, very different. Some things are going to look like similar to regular summation, but other things are going to be completely outside of the operation done with scalars. Okay, so let's see. First, we need the representation of vectors. Let's take a look at the representations of vectors. A graphical illustration of vectors so you can have a qualitative idea how vectors work. Okay, a graphical operation of vectors. A vector is represented graphically by an arrow. Okay, here you go. Here you go. Here's a vector. Here's one vector, and I go ahead and attach a mathematical symbol, mathematical letter to the vector. The vector A with an arrow there at the top. Okay, and this vector makes a even angle with the horizontal direction. Okay, and I can denote this angle as being the angle theta. In this case, I have chosen the reference of the angle in terms of this horizontal direction. I can define a vertical direction angle with respect to the vertical direction as well if I want, okay? The magnitude of the vector is represented by the length of the arrow. Okay, the intensity of the vector is represented by the length of the vector. Those two vectors, even though I labeled them with different names, with different letters, they end up being equal. They end up being equal because they have the same lengths and the same direction, even though they are positioned at different places. Okay? So here you go. I can copy and paste here. I'm going to see that those two vectors have exactly the same lengths, right? And because they have exactly the same length and the same direction, they are equal to each other. But these other two vectors, they are different. They are different because one, the magnitude of one is greater than the magnitude of the other, even though their directions is the same. Direction is the same, right? Same direction, but different lengths. So let's write that down here in the notes first before we move forward. Oh, here we go. Vectors can be represented graphically as an arrow. The length of the arrow illustrate the intensity of the vector, and its angle with respect to a given axis represents its direction. Here you go. I'm going to put it this way. One, the length of the arrow illustrates the intensity of the vector. And the angle, the vector the vector makes with a given direction, represent it with a given axis, represents its direction. And that's what I have up there. Okay. If two vectors have the same direction and the same length, comma, these two vectors are equal to each other, irrespectively whether they are positioned at different places. Okay. Just like I said, the previous vector here, we have vector A and B that are positioned at different places, but they're still equal to each other because they have the same length and the same angle with respect to the horizontal direction. Okay. If a vector, here you go, if two vectors have the same direction but different length, then these two vectors are different. Likewise, if two vectors have the same lengths but different directions, they are also different. Oops. Okay, keep go. Different vectors again. Okay. This vector is different from this one because this one is phased out by 180 degrees. Even though they have the same magnitude, they're written with the same letter, they're still different because they have different directions. Okay, that's why I put this negative sign here. Vector A points towards the right, a combination of right and upward direction, right? The vector minus A points to the left or to a combination of left and downward directions. All different vectors. A, B, C, D, they're all different from each other. Okay. Now, let's talk about operation with vectors. We talked about, vectorial representation. Graphical representation of vectors. Graphical representation of vectors. Equality between vectors, right? Inequality between vectors. Then two vectors that have different lengths and directions are also different. Operations with vectors. The simplest operation with vector the simplest the simplest operation with vectors are the multiplication. First, the multiplication, right? The simplest operation with vectors. The simple operation with a vector is its multiplication with a scalar quantity. Okay, that's the simplest operation that we're going to see out there. At the beginning, that when we're learning math, right? The first operation that the teacher introduces us is the summation, right? Because the simplest one to do is numbers. But with vectors, it's different. It's the multiplication that's the simplest operation. But the multiplication between a vector and a scalar quantity, you cannot, by the way, you cannot multiply a vector with another one. Okay? There's no such a thing. Okay? So examples, right? Examples. Okay, here you go. One, we can multiply a scalar, which I'm going to name it as the letter C, with a vector, italicized, with a vector. And let me show you what happens when we multiply a scalar with a vector. Okay, if this scalar is greater than 1, then the resulting vector is longer than the original vector. Simple enough, right? So here you go. We have the vector A. I decided to multiply the vector A by a scalar that's greater than 1. Consequently, the resulting vector became longer, and I called this vector E. On the other hand, if the scalar is less than 1 and greater than 0, then the vector becomes shorter. The scalar multiplication does not affect the direction of the vector, only its length. Okay, but if C is greater than 1, right, it's longer than the original vector. If C is greater than 0, let's put a greater than 0 here on the left, 0 on the left side, okay? It's easier to understand, right? And less than 1, then the resulting vector is shorter than the original vector. In the two cases, in the above two cases, comma, the multiplication does not affect the direction of the vector. Oh, wait. I am trying to get this student in, but I cannot see the. Huh. Strange. Oh, here you go. Finally got it. Yeah, okay. Good. So going back here. Good. In the above two cases, the multiplication does not affect the direction of the vector. However, if C is less than 0, then the resulting vector, the direction, okay, the direction of the resulting vector will be changed by 180 degrees, just like you saw before, right? Go. It's just a repetition, right? Oh, and then we can also divide two vectors, right? Divide a vector by a scalar, not divide two vectors. Okay, multiplication, operation with vectors. Okay. Multiplication with a scalar. I'm gonna put it like bold-faced and italicized. Division by a scalar. It's not much different from multiplication, right? The division by a scalar is just the multiplication by the inverse of the scalar. Okay? A division by a scalar is not much different from the operation of multiplication, since it is the multiplication by the inverse of the scalar, right? Scalar. So you can say that a vector can be divided by a scalar, let's say C, or you can say that a vector can be multiplied by the inverse of C. Okay? We can say that a vector, a division by scalar is not much different from the multiplication with a scalar. With a scalar. E.g., I'm going to put it like this way, e.g., right? For instance, on 1, we can say that a vector can be divided by scalar C, or we can also say that a vector can be multiplied by the inverse of C. Either way, you get the same result. Either way. Either way, you get the same result. Okay? Here, you go. We can divide a vector by a scalar, right? R divided by C. C is a scalar. And similarly, we don't need a number here. Here you go. 1. If C is greater than 1, comma, the vector becomes shorter. Shorter, no, longer, becomes longer, right? Wait a minute. Yeah, it becomes shorter. What I'm talking about? I'm dividing, I'm not multiplying. If C is greater than 0, less than 1, then the resulting vector becomes longer than the original vector. Oh, and we have the other situation too, right? If C is less than 0, then the direction of the results vector will be changed by 180 degrees, just like we had for multiplication. Let's see. Here you go. Division by C greater than 1, division by A scalar between 0 and 1. And let me put another one here. Now I'm going to do the following. Here you go. I'm going to invert the direction of this vector. Can I do that? No, not here. Let's see if I can get it the right one. Format, size, and position. No, should be format. Yeah. And here you go. And now, let's see here. In this specific case, the angle of the vector is measured like that. Okay, and now I'm going to call that, since it's a different angle, that's how you actually measure the direction of a vector. Oh. Symbol. Yeah, I'm going to call it theta prime. Like that. Okay, and in this case, the vector C, the scalar C is less than -1. Okay, less than -1 because it's longer. I'm going to do the same for this one. I'm going to invert the direction of my vector. But in this case, the scalar is going to be less, you know what? I'm going to put -1 here. Greater than -1, less than 0. Just like before, the angle here is measured with respect to the tail of the vector. And I can, here you go. Like that. I'll put my theta prime right here. Let me see, I'm multiplying, right? So, and I need to, one more student here. Let's get him in. Like that. Okay. And I'm gonna shrink this guy here so you do not get confused. And I wanna view the grid lines. Like that. Like that. Like that. And then we can do the same for this one here, right? Let's see if I can just copy this one. Yeah, let's just copy this one. And that's gonna be division, right? By scalar number. Division by scalar number. If, let's see. And then I have to put this guy here divided by C. No longer multiply it. If C is less than 0 and greater than 1, less than 0 and greater, no, less than 0 and greater than -1, right? We're dividing by a number. Then the vector becomes longer. Let's put it this way. Now, if A is less than -1, then the vector shrinks. Not only changes direction, but shrinks. It's better even to put like that, you know. Like that. Good. And let me, okay. Okay, so 2, 3, 4, here you go. Operation with vectors. Vector A, vector E, which is A multiplied by a scalar greater than 1. Vector F, which is vector A multiplied by a scalar less than 1. Now we're going to do this operation with negative numbers, negative scalars. A scalar that less than -1 changes the direction of the vector, and on the top of that makes it longer. If the scalar is greater than -1 and less than 0, this operation makes the vector become shorter, and on the top of that changes its direction as well. Division is all the way around, right? If the scalar is a positive number greater than 1, when you divide the vector by the scalar, the vector becomes shorter. The resulting vector E becomes shorter. If the scalar is between 0 and 1. When you divide the original vector A, the resulting vector F becomes longer. Okay, and all the way around, original vector A divided by a negative number that between 0 and -1, vector becomes longer and change direction 180 degrees. Here should be divided, right? If the number is, if the scalar is less than -1, then the vector shrinks in size and change direction as well. All sorts of different operations, right? So here you go. Some operations with actual numbers. Right? I am multiplying the vector A examples by, I'm dividing, let's say I'm multiplying, right, the vector A by the number half, or I'm dividing the vector A by the number 2. The resulting vector is shorter. Multiplying by 2, the resulting vector is longer, and so on. -1, resulting vector becomes the same size, continues the same size, but its angle changes by 180 degrees. Same thing here, but now the length of the vector increased. Okay? By the same token that we here, what I have done is just to illustrate two-dimensional vectors. But we can also have three-dimensional vectors, and that's how we represent them. We represent them to give the, in this way, to give the illusion that we have a three-dimensional space. Axis, X, Y, and Z. Okay. And they should be oriented in this fashion. Positive is in the direction of the arrow points. Positive X, positive Y, positive Z, right? Here is negative X, negative Y, and negative Z. And if this vector is in the three-dimensional space, that's how we represent it. Okay, this component here that you see, here's the vector A in the three-dimensional space. When you project the vector in the XY plane, right, we have this component of the vector in the XY plane. And we can also project this vector in the z-axis, along the z-axis. Let me illustrate that for you. Here you go. I'm going to illustrate that, the vector, and I'm going to dash it so you don't get confused. The dashes is a representation of the component. Subscript XY. I represent it this way. Mathematically. Italic, but okay. But this component also can be projected along the x-axis. Let's put that in different colors. Let's put that in different colors so it becomes easier. Wow, that's terrible. Green. Green. Yeah. Let's see this one. Which color? Blue. Yeah, let's put blue, blue. And then we have this other component, the Y component. The Y component right in here. And which color? Let's use this one here. And this other one here. Here you go. And finally, we have the Z component. Which color? Which color? I see black. No, I don't want a black. This one? Yeah, this one is different, right? Here you go. And call it Z component, A sub Z component. It's still a vector. This one? Yeah. Okay. Now, let's talk about summation. So we covered multiplication and division. Multiplication and division with and by a scalar, right? We covered vectorial multiplication and division with and by a scalar, respectively. I'm going to emphasize here the following operations are not allowed. There's no way for you to, let's say, multiply a vector by another. Here you go. Okay, not allowed. One vector divided by another. Now, let's talk about the third type of operation. Summation between vectors. Okay, and the summation between vectors is represented by the following operation. I'm going to sum vector A with vector B. Okay, that's how we represent mathematically. So let's say A plus B results in a different vector that we call C. Okay? But the simplest of all summation, simple of all summation operation between vectors is this one. A plus itself. A plus itself results in the vector 2A. And we have the same thing for B plus itself, right? Results on the vector 2B. Okay. So when we sum two vectors, we can use two different graphical methods to determine the resulting vector. Can you remember that? The head to tail method and the parallelogram method. And the summation between vectors is commutative, has the commutative property. Commutative property. What does it mean? A plus B is equal to B plus A. Like that. Okay? Unlike, right? Unlike the multiplication and division with a scalar, right? Let's write that down here. Both division by scalar. This operation is not commutative, right? Oops. This operation is not commutative. However, the summation between vectors is an operation that is commutative. What does it mean? It means that R divided by C is different, right? Let's put the different sign here. Is different from C divided by R. Is different from, not only is different, but this operation here is not allowed. Not only the above inequality holds, but on the top of that, comma, the operation C divided by R is not allowed. Is not allowed. Not allowed. We have the same thing for multiplication, right? So you gotta be careful. This operation does not commute. Okay, so what does it mean? C. Wait a minute. Oh yeah, this operation does commute. Yeah, this operation does commute. Okay, does commute. It's just the division that doesn't commute. Okay, here goes C dot R is equal to R dot C. But not the division. The division doesn't commute. They are equal, but we usually represent this multiplication by this one here. We always put the scalar in front of the, it doesn't mean that this one is incorrect. No, this one is correct, okay? Let's see how we can represent. What time is that? 2:35. Can go another 5 minutes, right? Let's represent graphically. How do we sum the vectors to different vectors, okay? Operation with vectors graphically is either the head-to-tail method or the parallelogram method that I mentioned. When we are summing two vectors that are equal to each other, the parallelogram method doesn't work. We gotta use the head-to-tail method, okay? The head-to-tail method is exactly what the name says. We put the head on one vector at the tail of the other, okay? That's what we do. And let's see if I can do a movie here. Play a little movie. We start operation with vectors. Here you go. Sum between two vectors. I can go even further than that, right? I can put the vector here. Start with just the arrow. I'm exaggerating here, right? Put the name of the vector, just to give time for you to copy. Get the horizontal direction and measure. Oh, I copy this one. You go first. Get this horizontal direction and name the horizontal direction, right? Vector, arrow, A, horizontal direction, angle. And now I'm going to do what? I'm going to sum A plus A vector, right? So you go A plus A vector. A plus A vector. And I'm going to write that down here on the right side. I already know that's 2A. 2A. So how do we do it? We get one A vector. You know what? I'm going to put it in the same. Let's see if it fits, right? Let's put right in here. A vector. This guy goes here. Let's see. Just commute, right? Commute it. You go like that. You go. The angle is the same. Let me copy and paste that. No, first I gotta copy and paste this one. Yeah. Shrink it. Put a little bit to the side. Then I write it down. Sum between vectors. Head to tail method. Head to tail method. Oh, play the movie again. You got vector. Name it. Orientation. Angle. Okay. Reference axis, right? Reference axis, angle. Then we want to sum it's the vectors itself, the simplest operation that you're going to see out there, summation operation, right? Here you go. We place the vector A a little bit to the right. Don't forget to add the orientation. And then what do we do next? We apply the head to tail method. The head to tail method consists of placing the other vector, the tail of the other vector, at the head of the other one, of the first one. And I can hiccup. And I'm going to do the following. I'm going to put it right in here. And then the resulting vector. Oh, the resulting vector can be drawn as being, here you go. Let me see if I can rotate it. Here you go. Yeah, we can rotate it. Make sure I'm using that just as a reference. Yeah, good. Go a little bit here. And I'm going to get my reference line. Yeah, and I'm gonna dash it. Dash it again on the other side. Okay, here we go. And we have the resulting vector going. I'm going to increase the size. Let's see if I can increase the size. Format. Here you go. Yeah. Let's see if I can do that. Okay, better like that. That's the 2A vector. Here we are doing just in a graphical sense because it's more intuitive. Later on, we are going to do in a mathematical way. Okay. Someone is trying to come in. 243. Okay. Head to tail method. Let's play the movie again. Vector. Name of the vector. Reference axis. Angle with respect to the reference axis. We want to obtain the A plus 1A vector, which is the simplest summation that you're gonna ever see in your life between vectors. Okay? A plus A. So how do we do? We display our first vector, right, which has an angle theta with respect to the reference axis. Don't forget to name it. And then we use the head to tail method. We get the second A vector, put its tail at the tip of the head of the other. Or you can put it the other way too, because it's commutative, the operation, right? You can either do that, or you can do that. Put the head of the vector, of the second vector, at the tail of the first one. Either way it works. This angle here is equal to this angle. And then we draw the resulting vector as being this one here. Okay, and I can even do the same drawing for the other one, right? You go. You go. I don't need that anymore. I displace this one here. Displace this one here. It's a little bit off, right? Let's see if we can fix it. It's a little bit off. Barely off. Yeah, now we have it right. Two A. Right? And now we don't need that anymore. 246. Okay, and let's take a little break now. It is. Now let me just show you the schedule, right? It's the schedule. We are doing here 20. We're on the 22nd. The exam is going to be on the 8th of October. 2 weeks and a half. 2 weeks and 2 days from now. The exam. This is our first lecture on vectors. Bold-faced. And then on Wednesday, we will continue with lab 1. Report still not due, but should be due the other Wednesday. Lab 1 due. Let's put here. Lab 1 due. Lab 1 report. Yeah. Lab 1 report due. And 247. Here you go. Break. 240. No, it's not 247. It's 10:45. Oh, why am I saying that? 10:48. Now it's 10:48. 10:48 a.m. to 11:03 a.m. Fix that. Any questions before we proceed? Okay. See you in the next few minutes, next 15 minutes. Okay, summation. Vectors. And a vector is a scalar. And the multiplication they both have a commutative property. It does not commutate. Which does not commutate. Okay, so I corrected here. And now let's take a look, right, at when we do something like that, it's just like a one-dimensional summation between two vectors, because the operation occurs just along this line, just along a single dimension. Okay. Now here you go, another summation between those two vectors, but now that those two vectors are different from each other. Unlike the previous example in which the two vectors were equal. Okay. So we have vectors A and B deployed along the horizontal direction, and we connect the tail of the B with the head of A. like I said, we obtain the vector C that's longer, right? A plus B. And A and B again. Okay, we can do, I'm doing the commutative property, right? I'm taking advantage of the commutative property. So you can see we get exactly the same vector. Same length, same direction. And I will fix this guy here. And let me fix this one as well. Head to tail method. We are not using the parallelogram method yet because the parallelogram method cannot be used whenever you sum two vectors that are in the same direction. Okay. Here we go. Now, what do we have here? Yeah. Here's the commutative property explained in a single slide. Okay. I can either put the vector A on the left and the vector B on the right, or the vector B on the left and the vector A on the right. We end up getting exactly the same thing. Okay. In this specific case, the magnitude, the length of the C vector coincides with the summation of the length of the vector A with the vector B, okay? Because this is a summation in a one-dimensional space with two vectors that point exactly in the same direction. But something like that does not always happen. Something like that does not always happen, okay? Let's see here what's going on here. That, huh, the heck's going on here? Let me try this one. Oh, change. Okay, good. Now it's better. Taking advantage of the commutative property. Okay, so let's break. Okay. Vectors that when you sum, when we sum two vectors that point in the same direction, we say that the summation is done in the one-dimensional space. This summation is done in the one-dimensional space. Okay? This is the simplest. This is the simplest type. In this case, you must use the head to tail method only. Okay? This is the simplest type of summation that you will see between vectors. Okay? In other words, consider two vectors A and B that point in the same direction. Okay? That point in the same direction. Their summation will be given by let's see here. Their summation will be given by, something like that, right? By a vector C, which, by the way, points in the same direction as the vector A and is multiplied by a scalar number that we have to find. Okay? So it's going to be something like that. The magnitude, let's see here. Yeah, this number, don't forget, because those vectors are pointing, because those two vectors, because they are both two vectors point in the same direction, comma, their magnitude, the magnitude of vector C will be given by, here you go, will be given by, I'm gonna put it like that, here you go, magnitude of two vectors that are summing, we represent by this symbol here, the bar, okay? It's gonna be given by something like that. Okay. And that is gonna be, and let's not forget that still equal to the magnitude of this vector, okay, which is equal to the magnitude of this vector, right? Furthermore, what you see right in here can be here. One is the vector, the other is scalar, right? So we can separate the vector from the scalar, okay? And this number C here, this scalar C, now can be here written in terms of the magnitude of the other two vectors, okay? Which is going to be, don't forget, now what you say are writing here, they're not vectors anymore. Now they are scalars because we are talking about the magnitude of them. The C here is going to be given by the summation of the two vectors divided by the magnitude of the vector A. Okay, like that. Which, by the way, this magnitude of C that you see here ends up in this specific case being equal to the scalar C. So what you have right here is that this scalar C is going to be given by this relation that you see right in here. The length of A plus the length of B divided by the length of A. Okay? And now, okay, that's what we did here was the simplest type of summation, summation between vector. Summation in the 1D space, okay? In the one-dimensional space. Summation between vectors in the one-dimensional space. And I will, like that. What about in the two-dimensional space? Summation between vectors in the two-dimensional, 2 and 3-dimensional spaces. Here you go. Now suppose that we have this vector A and this vector B, right? I want to sum them. Just like I told you before, you gotta use the head to tail method. Either the head to tail method that you already know, right? Or the parallelogram method. Okay, when we use the head to tail method, we connect the tail of the first vector to the head of the second vector. Okay. Vector A makes an angle theta with the horizontal. Vector B makes an angle phi with the horizontal. And here you go. That's the resulting vector that we end up getting. And the magnitude of this vector is not going to be necessarily equal to the magnitude. It's not going to be necessarily, no, which will not be equal to the magnitude of this plus the magnitude of the other, okay? So here you go. What about the parallelogram method? Start with the vector A. We have the vector B, step by step. You join the tail of the two vectors. And then from these two vectors that are joined by the tail, you draw a parallelogram, okay? You draw a parallelogram. How do you do it? Here you go. Here's the parallelogram I'm talking about. And I'm going to put it dashed so you don't think that there is a new vector that we are summing, okay? And here you go. This one. And this one. That's what I want. You go, oops. This one here. This one? No, can do better than that. Like that. And then there's one more step. We connect this vertex of the parallelogram to the other vertex of the parallelogram. Okay? Why do I have that here? I shouldn't be having it here. Okay, let's take it out. Here you go. That's the resulting vector. We don't need that. Let's play it again. Here you go. Vector A, vector B. In the parallelogram method, we join the tail of both vectors and draw a parallelogram from those two vectors. The resulting vector is going to be connecting the tail of the two vectors to the head of the other two vectors that make up the parallelogram. That's what you see here. Okay? And there is a, let's write it down here. If the two vectors are not aligned, their summation will be a little bit more complicated. In other words, okay, the will be, let's see, will be different. Let's put it this way. Will be a little bar, will be different and a little bit more complicated. In other words, that, hey, I'm gonna need this one here. Their summation, the magnitude of their summation will actually be less than that. Okay? Gonna be less than that. And we can calculate it using something that we call the cosine law, the law of the cosine, which is not a law, okay? It's just a theorem. I prefer to call it the cosine theorem. And then you go back to that drawing that you saw. Not this one, but this one here, in case you have never seen before. Suppose that we have a triangle like that. It's not a right angle triangle. It's a more generic triangle. This triangle has an angle gamma that's opposite to the side C. Okay. Okay, so here you go. I'm displaying the triangle here. Here are the vectors, right? BA plus B is C. Vector A plus B, vector A, B, and C makes up a triangle. That's why I'm no longer illustrating a vector, right? Just their magnitude, side C, side A, side B. There is this law of the cosine. Let me put it between quotes. It's not a law. I prefer to call it a theorem, but for some reason, books, they call it a law. Shouldn't be doing that. Okay. The simplest one that you're already familiar with, the simplest type of summation between vectors that you're already familiar is the one in which the A vector makes a 90-degree angle is the B vector. Okay. And you know exactly what this length is going to be, right? The hypotenuse of this triangle, the Pythagorean theorem, right? Whenever it's 90 degrees. Okay. And that's one special case of what you see here. One special case of what you see here. And we have another special case. A plus B, whenever A is from the right to the left and B from the left to the right, this C is going to be this little one here. The angle between the angle gamma in this specific case, okay, the angle gamma in this specific case, here you go, is going to be 0, right? So let me show you what I mean by that. I'm going to here too, we have a gamma. Let me prove to you. Okay, let's work on this triangle here, right? And let's come up with a special case of this triangle in which the angle gamma is 90 degrees. Okay? That's what we got there. And let me do some, oh gosh, let's see. I'm going to do something else here. I'm going to dash this guy. Yeah. And now that I dashed it, I'm going to rotate it so you can see how I got the angle gamma to become 90 degrees, right? Oh, here you go. That's my angle gamma. And now I don't need it dashed anymore. Just like playing the movie for you to understand better, right? Here you go. That was the previous A, right? And that's now my new A. That's my previous gamma, which I'm going to dash it as well, right? And that is going to be my previous C, right? And that's going to be my new C. Yeah, you go. Old C, new C. That's how I got this triangle that you see right here. Now my angle gamma became 90 degrees. That's a special case of this more generic triangle that you see here. And we have another special case too, like this one that you see, okay? In which the gamma is equal to 0 degrees, okay? How did I get this special case? This other special case, right? How did I get this other special case? A, is pointing the other direction. Let's see, we are gonna get this one dashed. Right? And we are going to rotate it. But we are going to rotate it to the point where the angle gamma becomes equal to, right, to 0. See that happening? Okay. And let's wow. Now gamma equal to 0. And then what happens to my C? My C vector becomes this other one, this short vector that you see right here. I'm going to put a little bit displaced, so it's easy to see all those vectors. Let's see here. Yeah, doesn't move. Why is that? Yeah, what about now? Yeah. Now we have the B vector here, the new A vector. The B vector didn't change, right? And the new C vector. And this one is going to be dashed. Okay. In this case, gamma is equal to 0 degrees. In this specific case, the magnitude of C is going to be the smallest possible one. Okay, it's going to be the smallest possible one. In this specific case, the magnitude of C, you already know, is going to be given by the Pythagorean theorem. Let's write that down. And then we have the other one that you saw, right? For any combination, for any summation of two different vectors, the magnitude of the summation is going to lie anywhere between a given value. Okay, so let's get that here. That's what I'm doing, so you can understand. Okay, for the summation of any two vectors, comma, the resulting magnitude, of the resulting vector will lie between the following values. The resulting of the magnitude of the resulting vector will be between the following values. The highest possible value is going to be this one that you see here. And then I'm going to put it equal, small or equal, right? And like that. But then we have a negative number. And here, I am assuming that A is, magnitude of A is greater than magnitude of B. Okay? That's going to be the upper value. And then you have everything else in between, right? One of the values in between is going to be given by that Pythagorean theorem. Here you go. If the two original vectors make an angle of 0 degrees, we have the following. Magnitude of A plus B is going to be equal to magnitude of A plus magnitude of B. If the two original vectors make an angle of 90 degrees, now you're going to have something different. You're going to have A square plus B, magnitude of B square, and on the top of that, you're going to have a square root as well. This is the Pythagorean theorem. The formula, 1, 2, 3, the formula of the Pythagorean theorem. On the other extreme, when A and B make an angle of 180 degrees, we have I'm going to use this one here. Okay, where we assume that magnitude of A is greater than magnitude of B. Okay. Or if, here you go, if, okay, or you can here write it down as being B minus A, right? If magnitude of A is less than magnitude of B. Oops, less than magnitude of B. Okay. Then we can have some examples, right? Numerical examples. 735. Did you get the idea? Okay, so we have all those possible values that you see here. At one extreme, the magnitude of A plus B is going to be magnitude of A plus magnitude of B, depending on the angle, of course. On the other extreme, you're going to have magnitude of this summation here. This magnitude here is going to be magnitude of A minus B. And along this spectrum of values, you're going to have this other one in between. Okay? So basically what we have is something like that. Let's go like that. This guy will lie like that. And even better, right? Now you no longer have equality here. Yeah. You have this inequality. Okay, but I still didn't tell you what is the actual magnitude of the resulting vector, right? I just said the range of values. I just told you the range of values. The actual value of this length here of my triangle is given by the law of the cosines, which I'm going to write for you right now. It's not difficult to memorize. It's not difficult to memorize, especially if you know those three different special conditions, right? So it's very similar to the Pythagorean theorem. There is only one adjustment that you have to make, okay? For any angle between vectors A and B, comma, the magnitude of C will be given by the law of the cosines, which is given by, here you go, A plus B squared is going to be given by A squared plus B squared, which is the part of the Pythagorean theorem. Then we have another term here. Up to here, you can memorize that easily, right? Because that's the Pythagorean theorem. But what would be the final term? Okay, the final term would be a minus sign here. Number 2, magnitude of A, magnitude of B, and because it is the law of the cosines, obviously you're going to have a cosine. And the cosine here, and the angle that you will use in there, is going to be the angle opposite to the side, like that, the gamma angle. Okay? Can you remember that? Okay, here's the gamma. So this length here, which is C, right? Or the magnitude of A plus B is going to be this square, minus 2 times this, times the cosine of this angle. Now let us test. Now let us test if this equation is correct, right? Let's test this equation is correct. Okay. 1, 4, 1, 4, gamma equal to 0. Okay. For gamma equal to 0, what we end up having here? We end up having, oh, here you go. For gamma equal to 0, we have 0 degree here. Well, strange. Okay, good. This term here is going to be 1, right? And we end up with something like that, which is equal to something like that. Put the B here. We do not have this term anymore. We have we identify this formula. See, square of the first is square of the second minus 2i the first times the second, right? So what do we have? We have something like that. Okay. And now we can here write out yeah. Okay, we don't need that. Yeah, here you go. Centralize. Should be centered. Yeah, it's centered. Good, it's centered. We have something like that. 8 more minutes to go, right? And then magnitude of A plus B is going to be this square root here. And this square root is exactly what we saw before. Is this term here, right? For gamma equal to 90 degrees, the lowest possible value. Now, for gamma equal to, let's see why this guy didn't put number 2 there. Okay, 90 degrees. We're going to have the Pythagorean theorem because this cosine is going to be 0 if this cosine is equal to 0, right? We get the Pythagorean theorem, which is we take advantage of this guy here. Let's see. This one. And then we have gamma 180 degrees. Well, gamma 180 degrees I didn't illustrate, right? But it's similar. 180 degrees. It's similar to what you saw before, right? Right in here. Gamma of 180 degrees. You know, if gamma is 180 degrees, it means that the angle between A and B is 0, okay? Make sense? Okay? So here you go. The other side of the, here you go, I'll put it right in here. We'll do exactly what I did before. Let's see. We'll do like that, right? start with that. What happened? The gamma angle. And now this guy is going to be rotated clockwise until it aligns with B. In this case, the gamma angle is 180, but the angle between A and B vectors is going to be 0, okay? It's just the way we are measuring the angles here. Let's see if they aligned. Now they are aligned. I'm going to need this guy here. I did that before. Yeah, I did that before, but I didn't do the. I didn't do the intermediary steps. Okay. Now you see that the gamma angle is 180 degrees, right? And I'm doing this step so you can be convinced that the angle is of gamma angle is 180 degrees. That's why I'm doing this step. Here you go. Here's the C. And I don't need the dashes. Wow. Yo, 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 yo. Like that. Wow. Like that. Huh? And for gamma equal, now we have the longest possible side. What time is that? 2 more minutes to go. Here we are testing, okay? Here we are testing this equation, if it's right or not. Let's see, 180 degrees. Oops. 180 degrees. Cosine of 180 degrees is -1. Right? We end up with plus 2AB and what this thing is equal to? This is equal to something like that, but now with a, I'm going to do like that here. With a plus sign here, right? Square of the first is square of the second, two times plus 2 times the first and the second. And the longest possible vectors in term, the longest possible result in term with respect to the angle between the two original vectors. A magnitude of A plus magnitude of B. Like that. Makes sense, right? So the equation works. This is easy to memorize. This is easy to memorize. This is easy to memorize, right? The only question is going to be a positive or negative one. You know, if you're in doubt whether it's a positive or negative one, you just do those 3 tests that I did. But it's going to be a negative one. And don't forget, it's the angle opposite to the side. It's not the angle that the two original vectors make with each other, okay? It's the angle opposite to the side. And let's see. Did I stop recording again? Uh-oh. Let's see. Yes, there will be a I'm gonna post that in Canvas. The edit is asking whether there will be a review sheet, or list of things to focus. Yes, there will be, and I'll be posting it in Canvas. Let me see if I stopped recording. It would be a shame if I stopped recording. We lost all those minutes, huh? No, it doesn't look like I did. No, I didn't stop recording. Okay, so it's still recording. Now we can pause the recording, right? I'm back here. Okay, so let's summarize what we have done so far. It's 12:08 right now. One, vector is a different type of number that carries information about their magnitude and direction. And that's the major difference between vectors and regular numbers, is the direction. Okay, consequently, it does not matter where you place a vector in the 3D space. 3D/2D, let's put it 2D/3D space. If you have two vectors A and B of same magnitude and direction placed at a different point, these vectors are considered to be the same. Okay, placed at different points in the 3D space, these vectors are considered to be equal. Okay, are considered to be equal to each other, irrespective of their placement. Vectors can be multiplied and divided by scalars. For instance, the 2a vector is nothing but a plus a or c time or 2 times a. Okay, where 2 is the scalar, where the number 2 is the scalar. Instead of summing them up, okay, for instance, the 2a vector is nothing. Yeah, let's keep it this way. Vectors of the same direction but distinct magnitude are different of each other. Likewise, vectors of the same magnitude but different directions are also different of each other. If you multiply a vector by a negative number, change its direction by 180 degrees. Okay. Show an example of the sum of two vectors that are equal, but you can also, sum two different vectors. We did that, right? Graphically, we represent the summation of two vectors by using the head to tail or the tail to head methods. In this method, you place the head of one vector to the tail of the other one. The resulting vector is the one that's drawn from the free tail to the free head, right? There's also the parallelogram method. Line up, touch, right? Contact the tails of the two vectors. Draw a parallelogram from these two vectors. Connect the two tails of the vector to the two heads on the other extreme of the parallelogram. What I didn't do yet is subtraction, right? But the subtraction is just a special case of the summation vector. In both in summation and in subtraction, let's say both in summation and in subtraction, vectors obey the commutative property. To subtract two vectors, you must sum A with the negative of B, or A plus minus B. We're going to do that right now. And then we can move forward with something else, right? Law of cosine apart to the other side of the triangle. Oh, by the way, the law of cosine is important to before we go into the vectors that are subtracted, right? But the law of the cosines also applies to the other sides of the triangle. Okay, so here you go. Length A, length B, length C, right? Opposite angle of C is gamma. Opposite angle of A is alpha. And opposite angle of B is beta. Alpha, beta, gamma. The first three letters of the Greek alphabet. We did that on purpose. Okay? And, okay, so here you go. And let me just write that down, the law of the cosines for the other angles, before we move to subtraction of vectors, right? Here you go. And I'm going to here write that okay, law of the cosines. Law of the cosines for different sides, right? Different sides. We did for the side C, and here I'm gonna call it C square equal, I'm gonna put in a different notation now, B square, okay, AB. But then the same formula applies for the other side as well. If you want to put the A square here, to find the A square, all you have to do is to use the B and C sides, okay? And the angle that you're going to put here is going to be the angle that's opposite to the side A. The same format, you're just changing the sides and the angle. And then we can do the same equation for the B side, right? Okay, go. B, I'm gonna use this one. B square. And then you replace the B by the C and the gamma by the beta. Okay. Going back to the triangle, right? Here you go. Here's the triangle. I want to put, I'm gonna do like that. Alpha. Right? And then we must have the gamma. And here you go. But now instead, oh yeah, I have already have B, A, B, C, right? A, B, C, alpha, beta, gamma. Law of the cosines, and now I can copy and paste this thing here. For illustration purposes. Okay, so like that. And now we can talk about the negative. What about subtraction, right? Summation between vectors. Subtraction between vectors. Subtraction between vectors in the three-dimensional spaces. Okay, there is no much secret here. If you understood how to sum the vectors, you will automatically understand how to subtract the vectors as well. I'm gonna use this one. Okay, so here you go. Instead of A plus B. Now let's do A minus B. Okay, A minus B is nothing but the sum between A and the vector minus B. And I'm going to put this vector minus B in parentheses. Okay? So if you learn how to sum two vectors, you already should know how to subtract two vectors as well. How do you do that? Let's go get here. I'm going to, I'll have to, so, okay. So let's say this one here is my B vector. Let's say this one here is my B vector. I want to subtract B from A. So what do? I draw my negative B vector, just like I did here, just by inverting the direction, right? And let me change also the arrow. I think this arrow here must be this one here. No. I think this arrow is much nicer, right? A plus minus B is going to be what? From the tail of the minus B vector to the head of the A vector, okay? And that's what I did here. Whoa. And then you have to know the angles, right? A, B, let's see what we have here. Yeah, I'm doing the parallelogram method, right? And that's the summation of the vectors A and B. And then you got that, right? So let me illustrate. Let two vectors A and B. Let two vectors A and B. Let two vectors A and B below, right? In order to find A minus B, comma, you do the following. One, you invert the direction of B, and two, connect the tail of the minus B vector with the head of the A vector. Okay, so the steps are this one right here. I inverted the B vector, right? Connect the tail of the B vector with the head of the A vector. This one here. everything here. And that's what's going to be my resulting A minus B vector. So you have the following methods. One, graphical method. Head to tail and parallelogram methods. And the law, I'm going to be put between quotes, of cosine method. Okay. There is another method that I like a lot. And let me show you where we are here right now in chapter 1. Vector addition subtraction. We did that law of cosine. Now I'm going to get into this one here. Components of a vector. Okay. That's the most powerful method of all of them. That's the one I like the most. Okay. Components of a vector. Okay. Vectorial components. I already showed you, gave you a glimpse of what components of a vector is all about. And now we are going to elaborate even more. We can express a given vector in terms of its component along the x, y, and z axis. Okay, not just x, y, and z axis. But we're going to stick to the two-dimensional vector. It's easy to draw. Okay, so here's an illustration of the components of a two-dimensional vector. This vector A can be written down in terms of its x component and its y component. And now we can even write it in a mathematical way as well. We can add, we can add this, we can write this A vector in terms of the other two vectors along the x and y directions. Do you agree with that? Right? That would be by parallelogram method, right? The vector starts here on the lower left and ends here on the upper right. The corners of the parallelogram. But there is another way that we can write those vectors. Okay? For instance, this vector here, we can write it down in terms of a scalar that I'm going to call A sub x. And by the way, this scalar can be either negative or positive number. And also in terms of a unit vector that lies along the x direction. Okay? That's we call it the unit vector. Here you go. And we denote it by this hat symbol. X hat is a notation, for a vector with a magnitude 1 that lies along the x direction. Okay? And we can do the same for the y vector. What we have here is a very useful definition. X hat and Y hat that you're going to see is a very useful definition. Okay, A sub Y is going to be a scalar A sub Y, that can be either positive or negative, times my unit vector along the Y direction. And both X hat and Y hat have a magnitude of 1. I'm going to show to, and by the way, some books have a different notation, have a different, not some, I would say most books, most undergraduate books have a different notation for these unit vectors, different notation for these unit vectors. Okay? Instead of X hat, they call them I hat. Okay? Instead of Y hat, they call them J hat. And if you're going into the three-dimensional space, the Z hat, they're gonna call it IJ, K, okay, K hat. Just like the alphabet, I, J, K, right? I prefer using this notation here. Even though most books use this, most undergraduate books use this notation here. In undergraduate school, they use this notation, IJK, but then when you get into graduate school, they make you unlearn the IJK notation and start teaching you with the XYZ notation, okay? So why don't you do it XYZ from the very beginning, right? What is a good illustration for these unit vectors? Let me show you. Okay, here's my AX vector, right? The component AY, the AX and AY, the two components. And here you go. That's how we represent those unit vectors. Those unit vectors point along, this unit vector here points along the x-axis, positive direction of the x-axis, and this other vector points along the positive direction of the y hat, of the y-axis. That's how you should visualize them. And like I said, it's a very useful definition. Let me see. Okay. And now, numerical example. Okay, let's go to for a numerical example. Let's say this A vector has an X component that's 2 meters to the right and 3 meters upwards. Okay. The question that's asked, what is the magnitude of this vector that you see right in here? Okay. That, let me take away the example, numerical example. Numerical example. Let the x and y components of my vector be 2 meters and 3 meters, respectively. Find the magnitude of the A vector. All you have to do is to apply the Pythagorean theorem. Ax squared plus ay squared. And we get a magnitude of 13 meters, square root of 13 meters. Then I can also ask, here you go, find magnitude of A vector. Now I'm going to give you another example. Instead of finding the magnitude now, find angle theta. Find angle theta of a vector. Just apply trigonometry, right? Let me copy that into my notes, okay? So here you go. So you can have that in the notes instead of here, in addition to have it here. Example. Add the A vector below A, right? Item A. Find magnitude of let the components of the A vector below. Find the magnitude of the A vector. Find angle theta of the A vector. That's the type of thing that's the type of problem that you may find. Solution. Right? I'm going to get that's what I want here. I want this formula. Save me on the work. Here you go. Magnitude of A square is going to be magnitude of the x component of the vector A square plus magnitude of the y component of the A vector square, right? Pythagorean theorem. Okay, according to the data given by the problem, right? A magnitude of AX is 2m. Magnitude of AY is 3 meters. Four meters square plus 9 meters square is 13 meters square. I want the magnitude, not just the square, right? Not just the square of the magnitude. And then I end up with square root of 3m squared, which is square root of 13 meters. Square root of 13 is something between 3 and 4. Around 3.5 maybe, right? What about B? Right? All you have to do is to look at this triangle. There's nothing fancy about calculating this angle, right? But you can see that the tangent of this angle is going to be 3 meters divided by 2 meters. Okay. Okay. Looking at the right angle triangle, we have tangent of theta is equal to let's see. Yeah, I gotta go here. Okay, magnitude of a y vector. No, I don't want to like that. A, okay, divided by magnitude of the a x vector. Erase this thing here. A y is 3 meters. AX is 2 meters. So we get, we have meter cancel out with meter. We have tangent of theta is 1.5. You take the inverse of this tangent and we get what? I can do that with my calculator. Point 0.5. The result is going to be in radians. Let's see here in degrees. Oh. Okay. Yeah, I'm getting 50 something degrees. 56 degrees. Approximately 56.3. Okay. That's the type of problem that you can see out there. 8 more minutes to go. Now let's go for another one. Here you go. B vector. Here you go. 1 unit in the vertical direction, 1 y hat, 3 units in the horizontal direction, 3 x hat. Okay. I'm going to, one way to write that vector. Another example. Here you go. One way to write this vector is by using the bx component, the x and y component, bx and by. This component is a vector, okay? It's a vector that's pointing in the x hat direction. Here you go. So if this is a vector, what you see here is a scalar, right? A scalar multiplied by a unit vector. Very useful notation, by the way. And you're going to see that. Another way of writing that down is just by visualizing this bx here. This bx along the horizontal direction, positive horizontal direction. And its length is going to be b cosine of theta prime, right? That should be theta prime. Okay? And the other will be b sine of theta prime, pointing in the positive direction. And now, okay, another example. Now you can say, find magnitude of b vector, just like we did for a, right? A b vector. Find angle that b makes is the x-axis. Solution. Okay, so all I gotta do here is just to copy and paste what I did here for the a vector. Okay, and then I'm going to be a slightly more complicated problem. Hopefully we have time to do all of that. Here is gonna be b instead of a, b square is bx square, by square, bx square. I forgot to put meters here. But I already put meters. It's supposed to be meters, okay? 3 meters square. The other is 1 meter. 9, 1, 10. So what we end up having is a square root of 10 meters. Uh, okay. Angle by dx. By is 1, dx is 3. 3, right? Yeah, it's 3. Take the arctangent of this value, and I get 18.5 degrees, 18.4 degrees. 18.4 degrees. And let's write it down prime, right? Should be prime here. I'm too lazy to do that now. You go. No. 18. And now what time is that? 3 more bands to go. Okay, so Another example. Find A plus B. Okay. Find A plus B, magnitude of A plus B. And the angle that the above vector makes with the horizontal. Solution. And now you're going to see why I like this so much, this notation. Okay. A vector. Let's write down the A vector first. I didn't write down the A vector, right? Yeah, I should have written down the A vector. Let's write it down. A vector. Solution. A vector is equal to 2m in the x hat direction plus 3 meters in the y hat direction, right? That's how we write the vector A. We do the same for the B vector. O B vector 3m in the x direction, 1 meter in the y direction. Yeah. So A plus B, straightforward, right? A plus, let's see, one more minute to go. A plus B is going to be 2m in the x hat direction, 3m in the y hat direction, plus 3m in the x direction, 1m in the y hat direction. What else can you do? You can bunch together those two. They have exactly the same vectors. Okay? Vectors in the same direction, they add just like regular numbers. Remember that? And then I'm going to emphasize here the other one, 3m and 1m, right? And then I can 2 plus 3, 5. 3 plus 1, 4. Take it away, 450. That's the first part of the problem. Next time we finish this example, all right? And I guess you can even do that yourself. You have enough knowledge to finish that, okay? So if you don't have any questions, that's 12:51 now. I have office hours right now. If you don't have any questions, we can meet again the day after tomorrow, Wednesday. Okay? See you on Wednesday.
Thank you.
Hey,
Okay.
Professor.